performed in 8 committee. So this committee's experiment is speed of sound in air. You see here our experimental setup. This is Konstup. We have a power supply, microsecond counter, pulse box, and also we have this one. This is for giving the pulses also. So here, let's define the sound. Sound is a kind of mechanical energy. As you remember, we talked about this in our class, at our classes. So sound is a kind of energy, and velocity of sound in air is approximately 330 meters per second. And we need a media to transmit the sound waves. And actually, velocity of sound in solid bigger than velocity of liquid, and it's also bigger than velocity of gas. You see speed of sound in steel, water, and helium here. And let's look at the basic things about the sound waves. Sound wave is a kind of wave, longitudinal wave. We use sine waves to show the sound waves. And the unit of the sound is decibel. It's actually 1/10 of a bell. The name of it comes from Alexander Graham Bell. And this is describing this wavelength. You see here 1/2 wavelength, 2/2 wavelength, 1 complete wavelength, and 3/2 wavelength of this sound wave. And I want to remind you wavelength frequency definitions. Wavelength, length of a complete wave, which contains 2/2 wavelength, and then frequency is number of waves that pass a point during a certain time period. And amplitude, as you see here, distance from the origin to true or chest. So you see here frequencies in 1 second. You see 4 cycles, 12 cycles, 36 cycles. So 36 cycles per second gives us the 36 hertz. And the relation between frequency and the wavelength is, as you see here, in terms of speed of sound, of course. So frequency times wavelength will give you the speed of sound. Also, distance over time will help us to calculate the speed of sound. To calculate or to measure speed of sound, we will use this experimental setup. As I said in our first slide, this is Konstup. So here we will measure the propagation time of second pulse between a microphone probes in Konstup and use the result to calculate the speed of sound. So we have probe microphone, which is the long one, and also we have microphone probe, which is short one. By changing the distance between these two, we will look at the time measurements actually. So Konstup consisted of a loudspeaker attached to a sound pulse generator at the end of the tube producing a sound wave, and the other end of tube blocked by movable piston carrying 2 microphones with adjustable distance between them. For changing distances, reaching the sound wave from the tip of the microphone to the other is measured and counted by microsound counter. So it will be measured automatically. We will measure the second values, okay? So for the change in distances, measured time will be recorded. So we will obtain a graph of the change in distance and time, which provides the standard wave pattern from which wavelength of the sound can be calculated. So the speed of sound is calculated as a gradient of the traveling distance S and the propagation time T, according to change in distances between the probes and measured time values. We will calculate speed of sound, and then so we will measure propagation time T and the sound wave propagation time T of sound pulses between 2 microphone probes spaced as a distance S, so we know the distance. And the pulse is produced by sudden movement of a loudspeaker diaphragm controlled by a voltage pulse with step H. and high resolution measurement of the propagation time using a microsecond counter starts when the sound pulse reaches the microphone probes, and it stops when the second microphone probe at a distance reached. So the logic of the experiment is this. And again, you see the experimental setup here. Let's look at this. So we have this system, as you see. We have pulse box, we have microsecond counter, and we have microphone box, and you see long and short metallic structure, which are probes. We will adjust the distance between these, and we will take measurements here. So this is our experimental setup here, that we will take measurements. As you see, we can change the probe distance, and according to it, we will take the time measurement again as second. So after taking, by using different distances, after taking the time measurements, we will obtain distance versus time graph. And the slope of this graph, as in our previous experiment, we will use the slope, and the slope of this graph will give us the speed of sound actually. So it is possible to obtain very reasonable value for speed of sound in a single measurement, but a more accurate determination is achieved by varying distance between two microphones and by plotting the distance as a function of time delay between two channels. So the slope is directly the sound speed, by noting that the measured delay is proportional to the distance between the microphones, and one may conclude that the observed time delay is, in fact, the time travel of sound pulse between the microphones. So this slide shows you how you can calculate the slope, and then from here you can see the, according to distances and according to change in microsecond values, how we can calculate the value. And actually, you know, the experimental value of the speed of sound in air, 330 meters per second, and this will be your accepted value, and you will have an experimental value. You will calculate the percentage difference between them. So speed of sound, as you know, depends on medium temperature, and then of course our room temperature can be different than the normal 0 Celsius degree value, as you know. So 331 is for air, which is at 0 Celsius degree. So this can be the reason, the difference of it. So the speed of wave depends upon properties of the medium which the wave is traveling, and two essential properties which affect the wave speed. The first one, inertial property, so the density of the material. The greater inertia part of the particles of the medium, the less responsive that will be interactions of the neighboring particles. In our courses, we told about the traveling of sound waves in air, how particles transmit the sound waves. If other factors are equal, a wave will travel faster in less dense material, and sound wave will travel faster in helium than air, because helium particles have less mass than the air particles. So this is important. The speed of wave depends upon the properties of the medium which the wave is traveling, and this will affect the wave speed. The other one, second one, is elastic properties. So related to the tendency of the material maintain its shape or not deform whenever a force stress is applied to it. Steel is rigid material with high elasticity. Its particles have strong interactions to prevent deformation and maintain its if a force or stress applied. And rubber band deforms and changes shape readily, and the phase of matter has significant impact upon the elastic properties of the medium. So solids have the strongest interaction between particles compared to liquids and gases. For this reason, longitudinal sound waves travel faster in solids than liquids and gases. So the speed of sound also affected by temperature. Why? the temperature will affect strength of the particle interaction. So it will affect the elastic property of the particles. Because of this, the speed increase will increase for each Celsius degree increase of the temperature. Okay, so there is a simple calculation here. What is the speed of sound in air when temperature is 25 Celsius degree? This is the formula that shows you how you can calculate the change in velocity according to the formula. Yes, that's all for the speed of sound experiment that we will perform in this committee. Okay, thank you.